In today's video, we're going to be talking about energy in terms of calculations for potential energy, kinetic energy, and then total mechanical energy. So kind of combining the two equations at that point. Energy is anything that has the ability to do work. So our SI unit of energy is going to be joules. Within energy, it can be transformed or transferred into different types. So we have kinetic and potential. Kinetic we think of as energy as movement, whereas potential is kind of stored energy. And we can also have different forms and different types. So you can see how it falls under to thermal and mechanical, or chemical and elastic, and there's many different other ones even than what's on this slide here. But just know that we can transform or transfer it kind of how we see fit or kind of how it needs to be. First, we're going to start off with potential energy. So again, this is just stored energy, and it all has to do with the shape, the position, or some type of condition of an object. So in terms of gravitational potential energy, this is specifically potential energy that's influenced by gravity. We have the generic formula PE equals mgh. So PE, of course, stands for potential energy, and here potential energy is measured in joules. Any energy is going to be measured in joules, which is abbreviated by a capital J. M stands for mass, and this is going to be in kilograms. G stands for gravity, and here on Earth, gravity is constant. It's 9.8 meters per second squared. And when we do these calculations, always assume 9.8 meters per second squared. Assume that we're on Earth unless you're specifically told otherwise. And if you are told otherwise, then you will be giving a specific gravity to go with that situation. And lastly, we have H, which is height. And so height is measured in meters. In terms of how our units end up being, if we have kilograms and we're multiplying mass, gravity, and height, this is kilograms times meter per second squared. This equals kilograms meters second square second, and all of this is going to correspond to 1 joule. So that's just kind of the breakdown and how we're getting these units. For our first problem, and again, I'm just going to make sure that we have all our units ready. So that's joules, mass is in kilograms, gravity is 9.8 meters per second squared, and then our height is going to be in meters, m. So calculate the gravitational potential energy of a 1,200 kilogram car at the top of a hill that is 42 meters high. So here we have PE, mgh. So we're trying to find the gravitational potential energy here. We know the mass, that's 1,200 kilograms. We know the height, that's 42 meters. And of course, we definitely know gravity. So all of our units here are correct to use this problem. So we can just plug it in. Potential energy equals 1,200 kilograms times 9.8 meters per second squared times 42 meters. So here our potential energy is going to be 493,920 joules. For the next problem, during a baseball game, the batter hits a pop fly. The 140-gram baseball has 12 joules of gravitational potential energy with respect to the ground at its maximum height. How high is the baseball? So it's asking us for height. So if we line up all the information we're given or what we know, gravity is 9.8 meters per second squared. Height is what we're trying to find. It gives us a mass of 140 grams and 12 joules of energy. In terms of units, grams is not the correct unit that we want. This needs to be in kilograms. So we need to convert that. And I know there's 1,000 grams in every kilogram. So grams cancels out, and this is going to leave us with 0.14 kilograms. And that's the value that we're going to need to use in order to solve for height. Now that we know all the correct information, we need to rearrange this formula. So we're trying to get height on a side by itself because that's what we're trying to solve for. So I'm going to divide both sides by mass and gravity, which will cancel out on the right-hand side. So height is going to equal potential energy divided by mass times gravity. Potential energy being 12 joules, not 120. And the mass is 0.14 kilograms times 9.8 meters per second squared. So here our height is going to equal 8.75 meters off the ground. Now we're going to switch gears to kinetic energy. So this is opposite of potential. Where potential is stored energy or energy of rest, kinetic energy is going to be energy due to an object's motion. So anything that's moving has some sort of kinetic energy. Kinetic energy relies on the mass and the speed, or most of the time we just say velocity. So our formula for kinetic energy is Ke equals 1/2 mv squared. Kinetic energy is always going to be in joules, capital J. M, this still stands for mass, and we still need to use units of kilograms. And then V is velocity, which is meters per second. I cannot stress to you enough, remember to square your velocity. That's where a lot of my students get in trouble, is they forget to square the velocity. So problem number 1, it says, would you rather get hit by Derek Brown, who is a football player, running at 5 meters per second, or would you rather get hit with a bullet moving at a speed of 1200 meters per second? In order to solve this, we're going to calculate the kinetic energy for both. Which one ultimately has the most kinetic energy? So kinetic energy, and we're going to do this of Derek Brown, equals 1/2 mv squared, 1/2 our mass, which is 47.4 kilograms. Our velocity is 5, and again, make sure we're squaring that velocity. This total energy comes out to be 1,843 joules. Let's do the kinetic energy of our bullet. So the first thing that I automatically see here is 20 grams. Grams is not something we're using in this formula. We have to convert that to kilograms. So that's going to be 0.02 kilograms. So 1/2 of the mass times the velocity squared. This is going to give us 14,400 joules. So the point of doing these problems is to really see how velocity, with it being squared, influences the problem. We have something that is much, much more massive, our football player, compared to the mass of our bullet. However, mass isn't going to be the extreme contributing factor here. Velocity is, and that's because ultimately we square velocity. So always keep that in mind when you're solving these problems, that velocity is going to contribute to the most of this problem in terms of how much energy output you get. Now let's keep moving with working more of these problems. So we have a 35 kilogram child, has 190 joules of kinetic energy after he sleds down a hill. While the child's speed, or what is the child's speed at the bottom of the hill? So now we're calculating velocity here. So if we line up all the information that we're given, we're trying to solve for velocity. We know the kinetic energy is 190 joules, and we know our child weighs 35 kilograms. So to work this out, I need to rearrange the problem to solve for velocity. The first thing that I want to do is get rid of the fraction. So if we're multiplying by 1/2, now we're going to be dividing both sides by 1/2. When you divide by a fraction, you can just as easily multiply by the reciprocal. So instead of dividing kinetic energy by 1/2, I'm just going to say 2 times kinetic energy, because the reciprocal of 1/2 is 2 over 1, which is 2. So 2 times the kinetic energy equals mass times velocity squared. I'm going to divide both sides by mass. This gives me velocity squared equals 2 times kinetic energy over mass. Now it's very important here that we're not trying to solve for the square of velocity. We are trying to solve for velocity. So in order to undo a square, you have to take the square root. So therefore we're going to take the square root of both sides. So our final formula here, let me draw a little line, is going to be velocity equals the square root of 2 times the kinetic energy divided by the object's mass. Everything we have is lined up in terms of units. We just need to plug in the numbers. So this is going to be 2 times 190 divided by 35, and it's going to be the square root of that whole entire product. Once we get that, it's going to be the square root of 10.86, which is going to equal about 3.3 meters per second. And that's going to be the child's speed at the bottom of the hill. Previously in this class, we've talked about the law of conservation of matter and the law of conservation of momentum, where we said things like matter or mass and momentum, they're conserved. They cannot be created or destroyed. We're going to extend that to also include energy. Energy cannot be created or destroyed. However, we can transfer it, whether that's from potential to kinetic or kinetic to potential. We can convert it, but it's still conserved. So the sum of the potential and kinetic energy of a system is going to ultimately equal total mechanical energy. So here's another important equation that we can kind of add to our equation arsenal as we move through these problems. In this first problem, we're really going to try and combine what we know about potential energy and how that converts into kinetic energy. So we have a Navy SEAL, and his gear has a mass about 150 kilograms. So we have a mass of 150 kilograms. If he jumps out of a helicopter at a height of 5 meters, so we have a height of 5 meters, what is his velocity when he hits the water? Now, in terms of equations that we know, or that we've learned so far, so we know potential energy equals mass times gravity times height, and we know kinetic energy equals 1/2 mv squared. In terms of total mechanical energy, that's the one we just introduced, total mechanical energy equals potential energy plus kinetic energy. We really need to think about these formulas when we solve this problem. We know that we have to solve for velocity. Out of these three formulas, really only one contains velocity, and that's the kinetic energy one. So thinking about that, ultimately, in order to solve this problem, we need to know a few things. We need to know the SEAL's mass, and we need to know his kinetic energy. Well, fortunately for us, the problem gives us the SEAL's mass. However, it does not give us the SEAL's kinetic energy. We got to try and find that based off of what we're given. And this is really where we need to think about how potential energy and kinetic energy relates to each other. So I'm going to draw a little picture here. So we have a helicopter. This is my illustration of a helicopter. Okay. And we have our Navy SEAL that's going to jump out of it. So currently he's sitting on the plane or the helicopter, and he's going to jump out of it into the water. If the SEAL is just standing on the helicopter, he doesn't have any kinetic energy. All that energy is potential. So all the energy as it stands right here is potential. Now, as soon as he takes that leap out of the helicopter, the Navy SEAL is moving. So if you're moving, that's all kinetic energy. So let's draw moving. Okay? And all of this is going to be kinetic energy. Well, we know energy is conserved. So in this case, we can say that the potential energy is going to be completely converted to the kinetic energy. So potential energy, once he jumps, is now going to equal his kinetic energy. So if we can find this potential energy, then we'll know the kinetic energy. And we can do that because we're given mass and height. When we solve for potential energy, PE equals mass times gravity times height. We're still on Earth, so we know the gravity is going to be 9.8 meters per second. Plugging in the mass, which is 150 kilograms, times gravity, which is 9.8 meters per second squared, and then times the height, which is 5 meters, we get a potential energy value of 7,350 joules. And again, this is going to equal our kinetic energy because of the law of conservation of energy. We can plug this value in down here, 7,350 joules. Now we know the two pieces to where we can rearrange the kinetic energy equation and solve for velocity. KE equals 1/2 mv squared. If we rearrange like we did on the previous slide, and if you want to go back, rewind that, look at it again how I rearranged it, please feel free to do so. Velocity equals the square root of 2 times the kinetic energy divided by the mass. We are just going to plug in our formulas now, or excuse me, our values. So 2 times the kinetic energy, which is 7,350 joules, divided by the mass, which is 150, equals the square root of 98. The square root of 98 equals a velocity of 9.8, and then our units for velocity is meters per second. For this problem, in terms of the law of conservation of energy, we're going to be looking at a ball bouncing. So how does the kinetic and potential energy change as the ball bounces? First, let me go ahead and write our formulas up here that we know. And then finally, our total mechanical energy, which is KE plus PE. It says, use the diagram to answer the following questions. The mass of the ball is 0.03 kilograms. Question A, what is the total mechanical energy of the ball at point A? And we're going to assume all energy is conserved, and this is really important because when we have something like this, a ball bouncing, we know eventually it's going to lose its energy because the ball stops. This is because some of that energy is lost due to heat or is lost due to friction. So if that's the case, we know not everything that we have energy-wise in the beginning is going to be the same at the end. However, if it says assume all energy is conserved, then we are going to assume that we're not losing anything to heat or friction. So for instance, whatever total mechanical energy we have at point A is also going to equal the total mechanical energy at point C, the total mechanical energy at E, and then the same for all of them really. Okay? And that's important because if energy is not all conserved, or if we don't say assume that, then these wouldn't be equal. The total mechanical energy would become less and less with each bounce. But this says assume all energy is conserved, so that's what we're going with. So it wants to know the total mechanical energy of the ball at part A. So total mechanical energy equals the kinetic energy plus, not equals, but plus the potential energy. Let's see if we have everything to solve this. So total mechanical energy equals kinetic energy. Well, kinetic energy is going to be 1/2 mv squared. The mass of this, it says, is 0.03 kilograms. Now, velocity, it doesn't give us a velocity. But here's the thing. The ball has not dropped at point A yet. The ball has not done anything. It's still at point A. Well, if it's still, that means the velocity is 0. Also, if it's still, it has no kinetic energy. It only has potential energy. So in terms of this kinetic energy term, if you have something multiplied by 0, this whole term is going to go to 0. There is no kinetic energy. It's all going to rely on potential energy, which the potential energy for this is going to be mass times gravity times height. Mass is 0.03 kilograms, gravity 9.8 meters per second squared, and then we have a height of 1.5 meters, and I got that height off the graph over here. 1.5 meters at the top, and you can kind of just estimate where the points are on the graph. That's perfectly fine. This should be 1.5 meters. Multiplying all these values out, we get total mechanical energy equals 0 joules from the kinetic energy plus 0.441 joules from the potential energy. Here, our total mechanical energy is going to equal 0.441 joules. And again, what this means at each one of these points, do a little bit of erasing here. If we assume all energy is conserved, each one of these points are going to have a total energy value of 0.441 joules. And again, this is total energy value. Okay? And I can label it for D, E, and F as well. So, question A, what is the total mechanical energy of the ball at point A? That's going to be 0.441 joules. Now it wants to know, what is the potential energy of a ball at point B? And again, we're assuming all energy is conserved. So looking at point B, and I'm going to switch up colors here. B, we know the total mechanical energy is going to be equal to 0.441 joules. We also know that this total mechanical energy equals PE plus KE. At the ground, all right, in terms of potential energy, how does this look? Well, if we think about potential energy, up at the very top, all of this is potential energy. Potential energy is very high. Kinetic energy is very low. As we go down, your ball is moving. So as we go down, your kinetic energy is going to increase, but your potential energy is going to decrease. As we go back up, your potential energy is going to increase and your kinetic energy is going to decrease. And this is going to keep flowing through the whole entire thing. So at the highest point, you have high potential energy. At the lowest point, you're going to have the most kinetic energy. With point B, we are at the lowest point. So our potential energy should be very low. Again, if you think about what the formula is, potential energy equals mass times gravity times height. Well, what is the height at point B? The height at point B is 0. If the height at point B is 0, that means this entire potential energy term is going to be 0 because anything multiplied by 0 is 0. So therefore, in terms of mechanical energy at this portion, we have, or at point B, we have the total mechanical energy equals potential energy, which is 0, plus kinetic energy. We know total mechanical energy is 0.441 joules, and so therefore that has to equal the kinetic energy also. So at point B, the kinetic energy is 0.441 joules. Question C. It says, compared to point A and C, what is the total mechanical energy at point E? And we just want to provide a qualitative answer. It says, assume some energy is lost to heat, friction, etc. So we're looking at, so let's see if I can get a different color here. We'll use purple. We're looking at point A point A, compared to point C. What is the difference in total mechanical energy? If energy we know is lost, in that case, at point A, the total mechanical energy is going to be greater than the total mechanical energy at point C. Let's look at our final example using the law of conservation of energy problems. We're going to look at this roller coaster diagram, and again, if we want to think qualitatively about how potential and kinetic energy looks through this, remember the total mechanical energy is going to be the same at all these points. So total mechanical energy remains the same. In terms of potential energy is going to be the greatest at the highest points, and kinetic energy is going to be the greatest at the lowest points. Let's try to answer these questions based off of this knowledge. Question A, at what point or letter is potential energy at a minimum? So which one of these points has the lowest potential energy? Well, we know, based off of what I just told you, that potential energy is the highest at the highest point. So that's going to rule out A, C, and D. Those are going to be our highest points. We have to look at the lowest point to figure out what the lowest potential energy is, and that's going to be our minimum. So at point B, we're only at 5 meters. And again, if you want to go through and do all the calculations for this using the PE equals mgh, the mass and your gravity are going to be the same. The mass of this car is 1,986 kilograms at each point. That's constant. Gravity is also constant. It's all coming down to this height factor. And the height is going to have the lowest potential energy at the lowest. So this would be point B. Question B, at what point is the potential energy at a maximum? Again, we can do this qualitatively. We don't actually have to work the problems. Your potential energy is going to be the maximum at the highest point on the graph. The highest point on the graph in this case is going to be at point A because it has the largest height of 25 meters. Question C, rank the points from highest kinetic energy to lowest kinetic energy. In terms of what kinetic energy means, kinetic energy is the highest at the lowest points. So it wants us to rank highest kinetic energy to lowest kinetic energy. That means I'm going to put the highest point on here as the highest kinetic energy, or excuse me, I think I missaid that. Kinetic energy is the highest at the lowest point. Kinetic energy is the highest at the lowest point. So at the lowest point, that's where kinetic energy is going to be its highest. Our lowest point on here is B first. Our second lowest point is D. Third lowest point is C. And our fourth lowest point is A. A is going to be our highest. And then lastly, question D, what is the kinetic energy at point B? So here we're actually looking for a value. So we want to know the kinetic energy. Kinetic energy equals 1/2 mv squared. I know the mass. I don't know velocity for this. So we're not going to be able to use this formula to solve this problem because I don't know a velocity. However, there is another formula that we have that we can use to solve for kinetic energy. And that's going to be total mechanical energy equals potential energy plus kinetic energy. So if I know potential energy and total mechanical energy, then I can solve for kinetic energy. So let's get to work on that. The first thing I want to do is solve for total mechanical energy. I need to do this at the highest point of the graph because I know at the highest point of the graph, over here, we're just starting. If we're just starting, our kinetic energy is going to be equal to 0. And therefore, everything is going to be potential energy. In terms of total mechanical energy, that equals 0 joules plus whatever the potential energy is, which is mass times gravity times height. The mass of this is going to be 1,986 kilograms. The gravity is 9.8 meters per second squared. and the height at this point is 25 meters. And again, the reason why I'm starting at point A is because the roller coaster has not started moving. At the rest of these points, that roller coaster is moving, so we won't be able to calculate total mechanical energy. Once we multiply all these numbers together, we get 486,570 joules. This is going to be our total mechanical energy as well as our potential energy. So total mechanical energy at this point equals 486,570 joules. That's going to stay the same. We're going to assume that no energy is lost. So at point B, the total mechanical energy equals 486,570 joules. We're still working with this main equation over here. We need to find the kinetic energy. We just found the total mechanical energy. Now we need to find the potential energy to solve this problem. So for the potential energy, we need to find the potential energy at this height. Potential energy equals mass times gravity times height. The mass is 1,986. Gravity is 9.8 meters per second squared. And height at this case is going to be 5 meters. Once we multiply all of these, we get 97,314 joules. We now both have potential energy and total mechanical energy, so we can rearrange this formula and we can solve for potential energy. Or excuse me, we can solve for kinetic energy. Kinetic energy equals total mechanical energy minus potential energy. I just rearranged the equation to have kinetic energy on a side by itself. The total mechanical energy equals 486,570 joules. The potential energy, we're going to subtract 97,314 joules. This gives us a kinetic energy value of 389,256 joules. This is going to be our final answer down here, 389,256 joules. Go back through these slides, work some of these problems on your own. Try to come back in a few days or in tomorrow. Try to do this problem by yourself. See if you're getting the same answer. And if you always have any questions, please feel free to email me. I am always here for help and for clarifications.